Hey guys, this is the last video in chapter 3, Problems in Stoichiometry. Now, whenever I say problems in stoichiometry, I'm really talking about the three last main ideas with chapter 3, and that's limiting reagent, percent yield, and theoretical yield. So we're going to start with limiting reagent, we'll talk about theoretical yield, and then percent yield at the end. So last time we talked about having too little milk to make a bunch of pancakes, right? We had 4 cups of milk here, and then we had a whole bunch of eggs and everything else, and so we ended up making 12 pancakes. But the reason why we were only able to make 12 was because the milk ran out first. We only had 4 cups of it, so we could only double the recipe instead of maybe tripling or quadrupling. So it ran out first, and so this limited the number of pancakes we could make, which means that this is the limiting ingredient in our cooking recipe. That's the limiting ingredient. And it's the same idea for limiting reagent. It's the one that runs out first. It's the one that gets used up first. It limits the amount of product, like the pancakes, that we can make. And so let's take a look. So that was pretty easy, right? I mean, we could definitely see 4 cups, of milk, and if we have like 1,000 of everything else, the milk runs out first. Now we can't just look at this, look at a reaction and tell what the limiting reagent is going to be. Here we have a reaction: 2H2 plus O2 makes 2 water, and I want to react 8.1 grams of hydrogen with 57.6 grams of oxygen. And I want to figure out what runs out first. Now just take a moment, look at the problem, and tell me which one, or not tell me, that would be kind of weird. Think about which one should run out first. A lot of you are going to say hydrogen, right? Because it's so small. Look how much oxygen we have. We have 57.6 grams, and we only have 8 grams of hydrogen. Well, what if I told you that hydrogen actually runs out first, or that that oxygen actually runs out first? Let's take a look at how this works. If we go back to our recipe thing, we can see that we need a whole lot more of the milk than we do like baking powder, only 3 tablespoons. That's a lot like what we're going to do with this. We have to compare their molar values to either each other or the product. I've seen people compare it where they compare it to each other, but we're going to compare it to the mass of water that it makes, because that's the definition, right? The reactant that limits the amount of product that gets made. So our first step is to convert these guys to moles. So we divide by their molar values. H2, 2.0 grams of H2 and 1 mole of H2. This one is 32.0 grams of O2 in 1 mole of O2. Now we're going to compare them to water, to our product. So to do that, we have to use the stoichiometric ratio like we talked about in the last video. So for this one, it takes 2 moles of hydrogen to make 2 moles of water, H2. For this one, it takes 1 mole of oxygen to make 2 moles of water. This is H2O. And then why don't we go ahead, we could end it there, because that's all we need to figure out that. But what I like students to do is to get in the habit of going ahead and writing it all out, going from mass to mass. And so we have 18.0 grams of water in 1 mole of water, and same thing for down here. And again, this last step isn't quite necessary. All we need to do is compare their molar values, but I like to get students in the habit of going ahead and doing the whole thing and writing everything out, just because it makes the calculation, if that's your habit, if that's the habit you're getting in, it makes the calculation whenever we put all these things together a lot easier. Because you may have a couple questions on limiting reagent, a couple questions on theoretical yield, but you're definitely going to have at least one major calculation question that's all 3: limiting reagent, theoretical yield, and percent yield. So doing this calculation, we should get somewhere around 72.9 grams of water if we reacted 8.1 grams of hydrogen. And for oxygen, we should get something like, finish putting this in here, 64.8 grams of water. Now what these numbers represent here, these represent the number or the amount of of water that would be produced if all of our reactant reacted. So if we had 8.1 grams of hydrogen and 1,000,000 grams of oxygen, the hydrogen will react and we form 72.9 grams of water. If all of the 8.1 grams of hydrogen reacts and we had as much oxygen. Vice versa for oxygen. If we had 57.6 grams of oxygen and 1,000,000 grams of hydrogen, we could form 64.8 grams of water. And remember, the definition for the limiting reagent is the reactant that limits the amount of product that can be made because it runs out first. So as this is going, what we're going to do is we're going to say, okay, oxygen produces only 64.8 grams of water, which is less than 72.9. So our limiting reagent, the one that runs out first, is oxygen. Okay, because it produces a smaller amount of our product, right? It limits the amount of product that can be made. Now we can do this another way, where we compare the two reactants, where we convert something like 57.6 grams of oxygen to hydrogen and see what we have. We can do that real quick. I'll just do this right here in the middle, just to show you the other way of doing it. And you can do it either way. So this is much the same, convert to moles first, but instead of going to water, we can compare it to hydrogen, where we have 1 mole of O2 forms 2 moles of hydrogen, and 1 mole of hydrogen we have 2 grams of hydrogen. And so if we do this, if we plug this in our calculator, we have 57.6 divided by 32 and multiply by 4, we should get 7.2 grams of hydrogen. What that means is that we would need 7.2 grams of hydrogen to get rid of 57.6 grams of oxygen, and we have 8.1 grams, so we'd have some left over. So that's another way of doing it. That's the way you would do it if you're asked how much is left over, because then you just have 8.1 minus 7.2, and you can see that you have 0.9 grams left over. So 2 ways of doing it. I like this way, just because it helps out with your theoretical yield, because you already have it. Now let's look at another example where we're given 2 products, and we're just asked for a limiting reagent. Now, the way that we did it previously, all you have to do is pick a product. Just make sure it goes to the same one, right? Now we have to figure out our molar mass for sodium chloride, which is 23 plus 35, so we have 58.45 grams NaCl in 1 mole of NaCl. And then all of these are 1-to-1 ratios, so 1 mole of NaCl forms 1 mole of AgCl. If we look at our molar mass for AgCl, we get 143, so 143.3 grams of AgCl in 1 mole of AgCl. Okay, we can figure out that. Now we have to do the same thing. So if we look at our molar mass for AgNO3, we get 169.87 grams of AgNO3 in 1 mole of AgNO3. And the rest of this is going to look pretty similar. 1 mole of silver nitrate makes 1 mole of silver chloride. And we have the same molar mass, 143.3 AgCl in 1 mole. Now we have to do our calculations. If we look at the top one, we would produce 97.6 grams of AgCl. If we look at the bottom one, we would form 87.92 grams of AgCl. So again, whichever one produces the smallest amount of product is our limiting reactant, which in this case is silver nitrate. So AgNO3 is the limiting reactant. And again, you could do it the other way as well. That would be fine. Now, what is, so that's limiting reactant, but what is the other two? We've got limiting reactant, theoretical yield, and percent yield. Well, the nice thing is, if you do it this way, theoretical yield is done for us. The theoretical yield is defined as the amount of product that you can theoretically make if you react all of your reactant. Now, to be fair, this never happens. You know, we don't ever really react 100% of our reactant. So the theoretical yield here, which is why it's theoretical, is just the amount of product that your limiting reactant produces. So silver nitrate was our limiting reactant. 87.92 is our theoretical yield. If we go back to the previous example, oxygen was our limiting reactant. 64.8 grams was our theoretical yield. So it's already done for you if you do it this way, which is nice. But keep the other way in mind just in case. And so the last one is percent yield, and it's pretty easy. If 64.8 grams was the theoretical yield for this same problem, so 64.8 grams was our theoretical yield, the percent yield is just a measure of how close we get to that theoretical yield. So you'll see it a lot of times as actual over theoretical times 100. Now, what we mean by actual is what we actually get in the lab, what we obtain in the experiment. So this would be 54.3 over 64.8 times 100, and we get our answer. And we get 83.8%. So that's percent yield, theoretical yield, and limiting reagent.